Today we'll look where the data actually comes from, which you see in the cockpit, and we will also see that it's not really the true parameter that you see often, but many times there's a good reason for that. It is very important that pilots trust their instruments and not their own intuition or their feeling. When you learn to fly on the instruments, blind flying basically, this is the first thing you have to let go, your intuition, because you don't want to end up following the situation that the pilot in this cartoon is experiencing. Today we have an enormous amount of information, as you saw in the glass cockpit, all integrated. This is quite a compelling picture, but there's also a risk. For instance, here we see two pilots discussing the accuracy of the altimeter, while perhaps it would have been better to look outside the window. And in fact, today in cockpits, this is a real issue, the amount of head-up and head-down time. And there have even been crashes as a result of both pilots being head-down instead of watching outside the window. The instruments show altitude, speed, position, heading, and we'll look at a few of these parameters. We'll start off with the primary flight display, which shows on this side, it shows the speed, and on the other side, it shows the altitude. And this is also the order in which we will discuss them. But let's have a look at the units first. Originally, navigation in aerospace stems from nautical navigation, the only other way in which we could travel the world before we started to fly. You can still see this in the units. We see, for instance, that the unit for distance that is used is the nautical mile, which is close to 2 kilometers, 1.852 meters. Do not confuse this with the imperial mile, or the land mile, which is only 1.6 kilometers on average. In aeronautics, if we talk about miles, we always refer to the nautical mile, so the 1852 meters. For altitude, we normally use the unit foot. So the altitude is expressed in feet, and 1 foot is 0.3048 meters. In our calculation, we want to use SI units, but when we talk about instrumentation, you have to know these units because this is what the pilots use and what they're used to, and this probably won't change very quickly. For speed, we see that the nautical mile per hour is used, and this is 1 knot, as we call it. 1852 meters divided by 3600 seconds, and this results in the conversion factor to meters per second, which is 0.51444. During exercises, the conversion factor will always be given. We do not require the students to know the conversion factors, but it is good to be aware of them, have this order of magnitude. For vertical speed, the unit feet per minute is used, and to get a feeling for it, a normal vertical speed in an airliner is 1,500, so 1,500 feet per minute is a sort of regular vertical speed, a common vertical speed. Often you hear also speed expressed in Mach, the Mach number. And this is basically the fraction of the speed of sound of which you fly. So Mach 0.5 means you fly half the speed of sound. Mach 2 means you fly twice the speed of sound. The speed of sound varies in the atmosphere with altitude, because the speed of sound is dependent of the temperature. And we see here the formula is the square root of gamma, which is 1.4, times the specific gas constant R, 287, times the temperature in Kelvin. Using this formula will allow you to calculate the speed of sound at any altitude. Using the airspeed and divided by the speed of sound will give you the Mach number for this current situation. I said that despite the units, there are different speeds and you don't always see the real speed. Let's start off to look at the influence of wind. During the age of ballooning, there was a Mr. Marvaux who once proposed to add rudders to the balloon, as you can see on this picture here. And he proposed to add these rudders to control where you would be going with the balloon. But it didn't work. And you might understand why if you think about the wind. If the balloon is moved by the air, that means that locally there is no wind. When you're underneath a balloon, you won't feel any wind because you move with the wind. This also means that the only speed that you will really feel when you are in aircraft is the speed relative to the air. So we have to make a difference to begin with speed between the airspeed and the ground speed. When flying, you can use navigation purposes to measure the ground speed, but the normal ways to measure speed will always give you the airspeed. So how do we measure the airspeed? Well, you may have seen on many airliners little tubes connected to the side of the fuselage, and they are called pitot tubes. And pitot tubes are important sensors for speed, altitude, and vertical speed. But how do they work, and what are the errors? Let's first look at how they measured speed in the old days. In the old days, they used a very simple mechanic device. We see here a spring which connects a little beam which is able to feel the wind locally. This spring will be stretched if the wind pushes the vane to the back. And by just looking at where it was relative to a scale, the pilot could, by looking to the side, because this is the direction where the wind comes from, looking to the side, he could see his speed. And basically what this speed meter did was it was measuring the force that the air pushed on this vane. So with which force the air pushed on this vane. And this is what is called the dynamic pressure. It's the pressure caused by the speed. Today's way of measuring speed is different, but uses basically the same principle. We saw the sensor, and if you look really close at the pitot tube, you will see it has a hole in the front, and this is where we can measure the dynamic pressure. And it comes out of this tube. So the air comes in here, and you will feel the pressure that you can sense at the back of this opening. There's also an opening on the side of a pitot tube, or sometimes somewhere else in the fuselage. And this is called the static opening. And there the air passes by, and you measure a lower pressure, which is called the static pressure. Well, the inside of the pitot tube also senses the static pressure. So this pressure that is inside this tube is called the total pressure. And the total pressure consists of the sum of the static pressure plus the dynamic pressure. For the dynamic pressure, sometimes the letter Q is used. And the dynamic pressure depends on speed in this way, half rho v squared. And Bernoulli, remember the law of Bernoulli, which said that the total pressure remains constant along a streamline. This means that if you stop the air, as the pitot tube does, that you will feel the total pressure, because then the speed relative to the plane has become zero. The static pressure is dependent on altitude. And this is relative to your airspeed. But we can also see that the air density is in there, which means it also depends on altitude. And this complicates things a little. So what the speed meter does is basically it measures the difference between the total pressure and the static pressure. And this way you get an indication for the dynamic pressure. And in fact, the static pressure is also used to measure the altitude. And we'll look at that later, but it's good to know that it's the same sensor. And the static pressure is also used to measure the vertical speed. And this is done by measuring it twice, once with a very narrow opening and the chamber with a larger opening, and by measuring the difference between these two pressures, you get an indication for the vertical speed. So with one pitot tube, you can measure a lot. But I said this half rho v squared is not just the airspeed, but it also contains this air density. Well, the trick of the speed measurement is that we basically ignore this. We assume always that the density is equal to the density at sea level, which is 1.225 kilogram per meter cubed. And this is the speed which we show, and we call this the equivalent airspeed. Equivalent airspeed. But in reality, we know that if we want to know the true airspeed, we should have taken the real density. Well, this relation is an important relation because it shows the difference between what's being shown, the equivalent airspeed, and what it really is, the true airspeed. And it also shows how you can change one in the other. For instance, from this relation, it shows that if we want to know the true airspeed, we basically take the square root of the density at sea level divided by the true density, or this should be the true one. I shouldn't use the index C here. Oops. So, like this. True times the equivalent airspeed. This is a relation to convert the equivalent airspeed, as you can measure it, to the true airspeed. However, in the cockpit, we show the equivalent airspeed. We do not do this conversion. And the reason is that the equivalent airspeed is the measure for the total dynamic pressure, which is far more important than the true airspeed. The dynamic pressure is what determines whether you will still fly, whether you fly too fast or too slow, whether the wings can still sustain the aircraft, or whether there is a risk of anything breaking off the aircraft. The dynamic pressure is much more important than the speed. It determines the performance, and that's why by default performance specifications, but also cockpit instruments, always talk about the equivalent airspeed. Well, not fully the equivalent airspeed, but something very close to the equivalent airspeed. Because if we look at the speed which we have the equivalent airspeed, but there's more speed. In fact, there are more effects. The pitot tube might not be in the correct position. There's an instrument error. So if we start all the way to the left with the indicated airspeed, the first thing we need to do is to take out the instrument error. And that is the calibration of the instrument and results in the calibrated airspeed, or CAS. Then there is an effect, a minor effect of compressibility, at least at low speeds. This is a minor effect because it really comes into play with substantial Mach numbers. And in our course, we ignore this. But there is in fact a conversion from calibrated to equivalent airspeed, which takes into account the compressibility. So in our course, we can assume that the equivalent airspeed and the indicated airspeed is the same. So we will use them instead of each other. And if I say indicated airspeed in an exercise, you can assume that this is equal to the equivalent airspeed. It's an ideal instrument and there's no compressibility. Then we saw that the relation between equivalent airspeed and true airspeed depends on the air density. And if you want to know the ground speed, you need to take the wind into account. To get the Mach number, you need the speed of sound, which also depends on altitude by the temperature. And this gives you the Mach number, the fraction of the speed of sound which you fly. So this means that the same true airspeed will result in a different Mach number for different altitudes. So we need to know the altitude as well. And this is exactly the topic of the next lecture on navigation and instruments.